Hello and good morning. I hope everyone's geared up and excited for this webinar today. I definitely am because this is a very relevant and important topic in today's world as we have increasing presence of solar PV panels in our system. So this webinar is all going to be about the impact of solar PV panels. How do you plan them? How do you size them? How much can your system accommodate? So that is the focus, and that brings me to the title, Introducing Solar Feeder Hosting in ETAP 2024. This is a new module, and this is a product of the Optimization and AI department of which I'm a part of. So I would like to acknowledge the team and thank them for their help in putting this together and putting the whole product together. So thanks to Raunak, Dr. Ahmed, and Dr. Fong. We have a pretty straightforward agenda today. I will introduce the topic and present some fundamental questions to better understand what the scope is, and present some motivations and challenges, why conventional techniques might fail, why do we need a study like this, and then focus on the product, what we offer, what analysis types we have available, what features you can incorporate when you model it, and what features are available for your result export and understanding of the analysis. And I will give you a quick product demonstration along with an example that is present in ETAP 2024 package. So some fundamental questions. What is a feeder? What does hosting capacity mean? And what is solar feeder hosting capacity? I will answer these first and then see how this is different from other types of hosting capacity, such as electric vehicle hosting. And once you understand the scope, you can better see what factors affect the modeling, what input you need to provide, what are the constraints that affect you, and what do the results mean, and then how best to optimize the results that you have and combine it with any other type of study that you want. So what is a feeder? A feeder fundamentally is a piece of electrical equipment or wire that's designed to distribute power from a substation or a utility to end users. It's an essential part of a distribution network, and you pretty much define it as the point that's immediately downstream of a substation or a utility. And this is typically radial and unbalanced. In ETAP, we use a high voltage circuit breaker element to model it. So in this example that you see here, I have the HPCB1 editor. And by selecting this association and designating it as a feeder, you can see that you have a tiny f that appears on the system. So then this would be defined as the feeder head, the starting point of the feeder. Now, distribution networks often require geographic information as well to model their systems better. So we have the concept of feeder available in the one-line view as well as the GIS view. And feeder hosting capacity, and as do some other calculation methods, support calculations for just the feeder that is selected or for the entire system. Now, what is feeder hosting capacity? So hosting capacity in simple terms is the ability of an electrical system to accommodate a new device while maintaining desirable operating standards. You could define hosting capacity for anything, for an elevator, for a room, for a stadium, because you want to mention what the size is and how many people it can accommodate. Similarly, if you want to bring about a new device in an electrical network, you have to assess how much of that new device can actually be hosted. An example of such a study is optimal capacitor placement. If you want to size your capacitors and place them, you have several things to check, like voltage constraints, power factor constraints, capacitor installation cost, capacitor size, number of banks. And that is a good example of a study like this. So extending that logic to PV arrays, solar feeder hosting capacity is essentially how many solar PV panels that you can accommodate in a system without violating its voltage without violating the power factor, or without overloading the system beyond reasonable means. we can extend this logic to also electric vehicle charging, which is very similar, because when we come down to sustainability studies, these things go hand in hand. So electric vehicle charging and electric vehicle hosting is related to, but is separate from solar feeder hosting, because then you're looking at a very different type of element there. So that would be EV hosting capacity. So in today's discussion, I will focus on solar feeder hosting. And our main character of the day is the PV array. So what factors affect an FXE study? So you have technical constraints such as voltage violations, thermal overloading, real power backflow, and minimum power factor requirements. You also may deal with relay miscoordination or short circuit injection from the inverter, or a harmonic distortion that might arise from the inverter. So you have several factors to look out for on the technical side, and these constraints will govern how much you can install and where. And aside from that, you have some non-technical constraints as well, as you would have to consider the cost of installation, things like tax rebates that you would get, and availability of space, because let's say you are looking to install over a certain building or over a certain car park, which is becoming increasingly common, then you don't have a lot of space. You have to judge how many panels you can place and determine the capacity at that point just based on the space requirements. So you have plenty of other things to consider besides, the technical aspects of it. Apart from these factors, how you model the system and how you model the most critical element in this context, the PV array and the inverter, that very much matters, because the inverter model in ETAP has plenty of control methods like voltage control, swing control, smart inverter control, MVAR control, power factor control, and different modes are appropriate for different needs. So you would have to consider the effect of the inverter control and its contribution in a very significant way, and they affect the results. Another important thing to consider is that feeder hosting capacity is a planning study. You would plan this out over several years. You can combine this with other types of analysis techniques like volt-var optimization control that are more conducive to real-time responses and real-time needs. So when you combine such optimization techniques together, you can achieve even greater results. So there are some challenges that accompany placement of a PV, as described in the earlier technical constraints. Voltage violations, thermal overloading, backflow are some of the challenges that exist when you place a PV. Now, trying to address these challenges in a traditional method would be very cumbersome, slow, and computationally expensive. So let me give you an example. In this case, I am looking at IEEE 123 node test distribution system, a modified version of it where some solar PV panels have been placed on some buses. And in this case, when you turn on 7 out of the 10 PV that are placed, you end up with some overvoltage in certain buses. As you can see, bus 451, bus 197, bus 72 report overvoltage. And a part of this reason is a lot of the PVs are a little too close to each other. So this puts the voltage profile of the system in an unfavorable position. However, in this case, we have one more PV that's brought into service, 8 instead of 7, but you still do not have voltage problems. And the reason is that they're a little more distributed than they were before. Now, to go about identifying this combination manually is going to be a little difficult. And this brings me to ETAP feeder hosting capacity. This module will help you do it automatically without having to model it for every single bus or every single situation and scenario that you want. So to give you an overview, ETAP feeder hosting capacity calculates optimal bus hosting capacity at a bus level and at a feeder level. In addition, it studies the impacts of DER penetration into systems, and it also considers new techniques and modeling capabilities like smart inverters. Therefore, you can enhance the performance of your system. We include constraints like thermal limits, voltage, power factor to provide reliable solutions. And by conducting FHC studies, utilities can optimize the placement and capacity of DERs. And a big boost about a big advantage of this module is that it's quite fast and it will save time, resources, and increase accuracy. A feeder hosting capacity is part of ETAP 2024, where we have recently transitioned from a classic toolbar interface to a more modern, stylish ribbon bar mode. So in this ribbon bar, you need to first use the feeder hosting capacity mode button to navigate into the mode. And once you are in there, you have three different analysis options: nodal feeder hosting capacity, DER optimization for feeder hosting capacity, and then impact analysis. So these three analysis techniques have their own similarities and differences. So we will first go over what they mean. So the first analysis, nodal feeder hosting capacity, is very straightforward. This is going to determine the maximum PV capacity that can be hosted at each node. This is going to consider every single three-phase bus that's in the feeder, and it will provide a reasonable solution if it is possible. And if no solution is possible, it will not provide you with a hosting capacity for that specific bus. This is an example of the IEEE 13 node feeder, and this question pretty much encapsulates the energy of this analysis type. How much DER can a specific bus accommodate? The second technique, stochastic or DER optimization, this will help evaluate the hosting capacity for the entire feeder or the selected feeder from a bigger picture. This analysis technique calculates the maximum and the minimum of the entire feeder by considering all possible combinations of buses that are selected as candidates, all possible sizes of penetrations at each of these buses, and it takes a probabilistic approach. By taking all the permutations and combinations of injections in various buses, you are able to come up with a scatter plot based solution that you can see to my right. This scatter plot is a result of the simulation, and each point here represents a certain combination of buses that have been selected to host PV, and that combination also includes the capacity of that bus. So once you have a wide solution set, you are able to generate a scatter plot of the hosting capacity versus the maximum voltage. Those are the parameters of this curve. And when you see it, you have a red line at 105, which is the critical overvoltage limit of 105%. This line will help demarcate the different regions of this curve, this graph. So firstly, we have the green region on the left-hand side. In this green region, all solution points and all penetrations are acceptable because the maximum voltage is under the critical limit of 105. The second region that we move forward to, yellow, this is a mix of acceptable and non-acceptable solution points because you have certain buses, certain combinations of buses that give you an over voltage, but certain provide unacceptable results in terms of less than 105%. So you could be either way depending on the combination that's chosen. And then you have the red region that's considered unacceptable because almost all of these combinations result in overvoltage of the system. So by seeing this demarcation between the green, yellow, and red, you're also able to determine two important thresholds. The first is the minimum hosting capacity, which is the border between the green and the yellow region. And the second is the maximum hosting capacity, which is the border between the yellow and the red region, as you see here. Finally, the third analysis type, impact analysis concept. Impact analysis evaluates the local impact of solar generation as PV penetration increases incrementally. So you want to see if you slowly increase the penetration, how is the voltage at that bus to which it's connected to is getting affected. So this helps you sort of micro-analyze problems when you implement other techniques and consistently know that some buses are being problematic, you can specifically narrow down your focus to that bus and study the impact. And to help mitigate the consequences of overvoltage, you can combine this with smart inverters, because smart inverters are capable of injecting and absorbing reactive power based on the control voltage that's provided, the curve that's provided. So this plot that you see here is a simple plot of penetration in increments of 10 from 0 to 2000 kilowatt and the accompanying voltage at that bus. What are the constraints? We've talked about voltage, overloading, minimum power factor. This is how we enforce it. This ETAP feeder hosting capacity study case editor has a constraint page, and by providing these settings and selecting the checkboxes that you want, this provides the constraints for the system, and then you can choose the analysis that you want. And these constraints are globally applied to all three types. Further discussing what features are available as an input in the study case, we come to DER locations, because an important aspect of stochastic optimization is the ability to provide and select candidates, define minimum and maximum PV power penetration for that. So this page of the study case editor, DER LOC, this will list all of the buses that are available downstream in that feeder, and you can select what you want as a candidate and define its limits so that then they will be processed for DER optimization. These result visualization. So once you perform your desired study, we have different types of result visualization techniques depending on what you need. We have the viewer, which provides a tabulated result of hosting capacities for different buses, minimum hosting capacity, maximum hosting capacity. We also provide Excel report with Python script with rooms for customization from users, so that you can use these reports for more formal presentations and for more formal requirements. And this will provide a very detailed results on what's going on. To visualize things on screen as you simulate them, we have one-line view annotations, and we have the plots. So we provide with a bunch of different options to interpret these results to your favor. An ETAP feeder hosting capacity is compatible in both one-line view and GIS view. So this picture that I'm showing to you is an example. And this example is available as part of ETAP 2024 package named example FHC. And I will be showing more of that soon. This is the one-line view of the system. This is the GIS view, and feeder hosting capacity can also operate in GIS platforms. So before I continue, I want to clarify a key difference between DER stochastic optimization and nodal hosting capacity, because they're both very similar in their approaches to calculating the minimum and maximum hosting capacities. So the main difference is that DER stochastic optimization is going to look at it from the entire system, whereas nodal hosting targets an individual bus. Stochastic optimization helps provide policy making on DER planning. If you are operating from the entire utility perspective, then you have a lot of control and you have a lot of options in the location and placement that really matters. Whereas if you are specifically looking at one particular bus or one particular area, then you only need to see how much locally you can accommodate. And that's what nodal hosting capacity is about. So having established this difference, now let me bring up the example FHC package that I was talking about. So moving over to product demonstration. Now let me open up ETAP and let me show you the example that we have for you. This project that you have here, this is example FHC. You can open and launch this as follows. It's as a part of tutorials and examples within the distribution example FHC. So this is the project that's on my background. So in this project, as you can see, we have two PVs here. There's one near bus 37 and there's one near bus 5. We will be using these two buses to study impact analysis. And for every other bus in the system and for the entire system as well, we will run all three analysis types to see what's going on. So let me run the nodal hosting capacity first. This is here. And before that, let me give you a quick tour of the study case editor, where you have options to select and apply for smart inverter. You have the DR location page where you can select multiple candidate buses for stochastic optimization. You have the impact analysis page where you can select the different devices you want to consider for impact. You have the constraint page where the different technical constraints will be enforced. So let me run the first button. Yeah, as you can see, our calculations have been completed. So let me zoom into some buses to see what results are being displayed. So you can see different buses here, bus 23, 35, 41. All of them have a head C equal to 1801 kilowatt or whatever the appropriate number is. This is the hosting capacity in real power. Now, what about reactive power? We considered by default a 90% power factor. However, you can change that when you apply minimum power factor constraints. And you can also change that when you have smart inverters incorporated. So let me just quickly change my display options to see hosting capacity with the reactive power. And then you can see how, considering 90% power factor that is supplied by the PVA, all of these buses can accommodate the number that's accompanying it on the annotations. You can also see this in the form of a tabulated result. So this, you see magnifying glass, FHC viewer. This FHC viewer, this table provides the total hosting capacity at each bus and what is the maximum voltage that occurs when said generation is placed on that bus, and where is the thermal limit occurring. In this example, almost all of the thermal limits seem to be occurring with the transformer. So, which is this. You can see the hosting capacity for different buses listed as follows. So this is a quick overview of how the first study works. And returning back to our presentation, you can see a quick comparison of what happens when you have different constraints or different input that you supply. So in the first image, we have a maximum voltage constraint of 102%. And in the second image, you have a maximum voltage constraint of 104%. Now, because you are raising the threshold for overvoltage, that automatically invites the space to put more PV. And therefore, you can see that the hosting capacity has increased. And similarly, if you were to modify your power factor constraints from 90 or 85 to something higher, if you want 95% power factor, you can enforce that. And when you do that, the reactive power that's supplied at the PV that's being suggested to be placed at each bus is also going to change. So in this case, you can see that both buses are at the same voltage of 105%, but the real and reactive power contribution is significantly different because of the power factor constraints that we have imposed. Let me bring ETAP again to show you how stochastic optimization works. So the second button is stochastic optimization. So let me run this and let me also generate the plot and see what we can do with it. Yeah, our stochastic optimization calculations have been completed. So now you can see that this icon is colored. It was previously grayed out. Now that we have something to plot, this is active. So let me click this. So this will only select output reports for which stochastic optimization has been performed recently. And that's why we have only one output report and not the other one. Let me select the feeder and let me see power versus percentage volt. So this would generate this plot for me, and let me maximize it. So as you can see, our minimum hosting capacity is somewhere around 2059 kilowatt, marked by this boundary between green and yellow. And our maximum hosting capacity is somewhere between 2800 and 2900, close to 2814 kilowatt. So each point here represents different combinations. So let me see what the labels for one of them are. So these results are also available through the FHC viewer. So let me go back to FHC viewer, and you can see that this provides the result. Minimum hosting capacity is close to 2064 and maximum loading capacity is 2816% kilowatt. So 2816 kilowatt, which is similar to the value that we've seen in the graph. Let me launch this again. Yes. Close to 2063, 2064, and this is around 2816. So that's how these regions are defined and marked. And you see this red line here over 105. This constraint line will also move up and down depending on what voltage constraint that you've chosen. And to see the details behind all of these points, the data is available in an Excel sheet. And that, let me tell you how to open. So this report is named HC2. You would have to go to your local the directory in which the project stored and open the Excel sheet of the same name. So in this case, it would be ETAP 2400, example FHC, and you see this hc2.csv. If I open this Excel sheet provides the details of all the combinations, what each point represents, what the random PV location is, and what injection is there at each of these buses. So as you go from top to bottom, you see more buses are being considered. And you can see that the hosting capacity, which is the first column, penetration, this is going to increase substantially from all the way till the last point, which is on the red region. So this way you can see all of the combinations that were considered. This is a probabilistic based method, so you will not necessarily get the same combination every time, but it has a very good degree of convergence and accuracy in the result. Returning to our presentation, I have here a capture of one plot where the thermal loading constraints have been slightly relaxed, in that the overloading is permitted to a slightly decent degree. And in that case, you can accommodate more PV. So you have a wider region and a higher penetration percentage, close to 135%. Whereas if you were to impose a much stricter thermal loading constraint, then that also limits your hosting capacity, and not all buses become then conducive. So your green and yellow regions will start to shrink. And even though in this case the penetration is slightly above 130, it's lesser than 135. This is about 131. Another factor that also plays into the performance is power factor. So in the DER location page of the study case editor, each bus you have an option to provide the power factor. So in this example, we have 85% power factor that is set as a standard for each bus, and that provides a minimum and maximum hosting capacity of close to 2099 and 2877 kilowatt respectively. However, if you were to change this power factor requirement to something higher, then you can accommodate more PV. So in this case, the power factor has been shifted to 90%, and therefore this affects your minimum and maximum hosting capacity as well. So the next analysis type is impact analysis. And before that, I would like to give you a quick overview of smart inverter and why we keep bringing that up as an important and powerful tool to help combat some reactive power problems. Now, a smart inverter is capable of injecting and absorbing reactive power, based on a certain control curve and based on the control modes that you offer. So there are several types of control modes such as volt var control, volt watt, watt PF, reference point power factor control. And the smart inverter also has some constraints of its own under which this curve will be valid and active, where you have some cutoff voltages and a maximum and minimum P max and Q max. You also have, so in this case, we are having a control curve from rule book, and this rule book is IEEE 1547 2018. So this volt var control mode, this curve provides a plot of voltage on the x-axis against the reactive power on the y-axis based on the percentage. As you can see that this curve is sloping downwards. So that means when the voltage is above 100, the Q is negative, and therefore this will absorb reactive power. Whereas if the voltage is less than 100%, then the Q is positive, in which case it would inject reactive power into the system. So by being sensitive to the voltage at that point, if you're experiencing over voltage or under voltage problems, you can use a smart inverter to adjust the reactive power and further take your hosting capacity to a higher level. So that brings me to impact analysis. And what impact analysis is all about is incrementally changing the generation of the solar PV and then seeing what the voltage at that bus is. And because voltage is so crucial to the operation of smart inverters, we can see how that plays out with and without using a smart inverter. So in this case, I have a power factor mode PV array operation. So let me open ETAP to demonstrate that for you. So let me run the third study, impact analysis. This impact analysis studies for this PV array PVA2 as well as PVA1 here. That's present here. So let me generate an Excel report that would tabulate all of the increments. So let me go to impact analysis and generate the report. You can see that this report is generated for each bus in different tabs. So for bus 37, we see that the PV penetration is slowly increased from 0 to 200 in steps of 10. And as this increment happens, the voltage gradually rises from 97.7 to 98.6. And a similar tale for bus 5, where the increment is from 0 to 100 in steps of 10, and we see the maximum voltage going from 99 to 9.21 to 99.57. Now, this might look like a very little change in voltage percentage, but when you have this is the impact of just one PV. But when you have so many PVs operating in tandem, and when you are unsure of how many to energize and how many to not energize, it might be advisable to, sort of micro-analyze, to just focus on one bus and see if a certain bus has too much of wild swings in voltage. So this study would be helpful to sort of break down problems location wise. So now let me generate new results by choosing to apply smart inverter. Impact 2. So let me compare. The table to the left is what we had when we ran impact analysis with a power factor mode, and the table to the right is with smart inverter. Now you can see that for as the penetration increases, the voltage also increases even with a smart inverter. However, it's not to the same degree. For example, this voltage of 98.31% is the maximum voltage when you can accommodate 200 kilowatt. But the same voltage of 98.31 is already achieved for 120 kilowatt when you have a power factor mode inverter. Therefore, what this really means is for the same voltage limit that you might impose, you can achieve a greater degree of penetration with a smart inverter, and that's because it has the ability to control the reactive power. Let me also compare with the other bus in this case. Yes. So as you can see here, at the maximum penetration, this a PF control inverter produces 99.57 voltage, maximum voltage, whereas the one using a smart inverter is able to offer a slightly lesser voltage. And therefore, this tells you that this can help bring down overvoltage problems and you can expand the hosting capacity. Now, before I continue, it's kind of important to realize that you can perform all of these three studies not only independently, but also make sense out of the results in one, but use it for another. For example, nodal hosting capacity gives you the maximum hosting capacity at each bus. Now, let's say bus 20 has a limit of 200 kilowatt, bus 21 has a limit of 250 kilowatt. Now, given this information, you can supply this as the minimum and maximum for stochastic optimization because you know how much maximum can be accommodated. And because you know that nodal hosting capacity considers all of the buses individually in a sort of a superposition way, that when you combine them, you cannot install the same level at all buses. So you may have your own planning parameters and factors where you can take the nodal hosting capacity results, downsize them to a certain degree, and provide that as minimum and maximum for your stochastic optimization. All of this is to say you can really narrow down the results if you can use one information, make sense out of it, and plug them into another as an input. As shown on my ETAP screen, this is another screen capture of impact analysis with the given control curve. You can see that in this case, we have modified the control curve to a much sharper profile. In this case, we are trying to center the voltage to 95% and make that the middle. And if it's over 95%, then we absorb reactive power. That's the goal of this sort of a curve. And this curve might seem a little counterintuitive to what we've done so far, because we've always wanted 105% as our maximum voltage. So you want support until then, but why is this at 95? Because there are techniques like volt-var optimization where you want to achieve some objectives like conservation voltage reduction or peak shaving. So you might want to operate the system at a lower voltage profile and bring everything down. So therefore, you might be tempted to use these types of smart inverter curves where the set point is set to 95 or something lower, because your operational objectives could be different. So in this case, even though we have 95% and power voltage given here, that's what provides this sort of a reactive power consumption. In this case, however, the set point is close to 100, but the voltage at bus 5 is less than that. So therefore, because it has not really met its overvoltage limit, it can supply reactive power to increase the voltage profile. And that's why in this case, we can see 43.4 kVAR that's being injected from the PV into the system. So this is my comparison of how you can best use smart inverter and other techniques to combine and get best possible results. I hope you found this informative, and I hope you want to experiment and play out with this module and play out with example FHC and see if you can bring something new to the table as customer requests, as customer tickets, or even as case studies. Thank you so much for watching.